Okay, so it's my pleasure to welcome our next speaker, Alexander Tovbis from University of Central Florida. And he will talk about Soliton and breather gases for integrable system, spectral theory, and its application.
Thank you very much, Thibault. I would like to thank all the organizers for it's quite an experience for me, this format of conference. So far the job is great. So thank you very much for organizing this thing and for inviting me. And I feel a little bit obligated from the previous speaker to give a good talk about the soliton and breather gases. So that is, so what I will report is a joint work with Gennady L. and Arno Kuilars from Leuven when it comes to proving existence of solutions of the equation of state and nonlinear dispersion relation. So there are so any movies that will be there and pictures are courtesy of Stefan Randu, Giacomo Roberti, and Elliot Blackstones. Let me start. So if the question is what is a soliton gas, that's a beautiful picture produced by Stefan, I think, about this is a circular gas, if I'm not mistaken. Maybe I will get to it. I have to confess that the time is 30 minutes, quite limited, and my ambition is try to explain how we get these equations describing soliton and breather gases, and report on what is known of when solution exists, what kind of solution exists, and stuff like that. So forgive me if I will be glossing over very fast. So basically, so when we talk about, so there were several talks about soliton gases, so I wouldn't repeat things, but one point I want to make: when we think about soliton gas, we can think about averages of large number of realizations. That means collections of in particular solitons. That's one way to think about it. And the other way is to take a special large genus limit, we call it thermodynamic limit of finite gap solution. And in this talk we will discuss the rigorous approach for the second option. So let me remind what is a nonlinear Schrödinger equation, and briefly speak about the simple solutions, such as plane wave solution, right? Q is a constant, the famous soliton solution, which is given by this formula. Then there are breather solutions, and one of them, Peregrine breather, is mentioned here. Then, of course, there are finite gap solutions that we cannot write as in a simple algebraic form, but they can be, this solution can be written in terms of Riemann theta functions. I will not need it in this talks. So, and finally, again, I want to emphasize that gases are, soliton gases are randomized large ensembles of the special solutions like solitons or breathers. Now, you've seen something in Stefan's talk. You see that there is a spectral portrait of each of the species that we talked before. For the plane wave, that is this, that is just the branch cut. For elliptic solution or genus 1 solution, these are two branch cuts. So everything, I have to say that everything in this talk, when it comes to the spectral theory, is Schwarz symmetrical. So there is a symmetry between upper and lower half plane. So if you have a elliptic solution and you want to contract the bands to points, So the solution will contract. So you extend the period and you will get a soliton at the end. Now, if you have genus 2 solution with bands like shown here, and you contract these two bands, you will end with one branch cut, one band, and 2 points, which corresponds to Breezer's solution. Now, these are the portraits of this is a soliton, and these are various Breezers. And I want to say that we can encounter them in they're not some exotic solution. You can encounter them in some physical situation. Stefan talked about this picture. This is the evolution of Sech potential, and you see the peregrine breezer as these little spikes around here as peregrine's breezer, and genus 2 solutions you see as a leading order approximation you see in those in this region and so on. So let's get to the core of the question, and that is the finite gap solution. So that's a picture of the amplitude of a finite gap solution. Here is genus 3. So geometrically, we want to think about a collection of bands and gaps, shown bands in blue and gaps in red dot, everything Schwarz symmetrical. And when we want to think about finite gap solutions, as I said, there are many ways to represent them. I prefer to, and it's easier for my purpose to represent them as a solution of a Riemann-Hilbert problem for the matrix Y of Z. Z is a spectral variable, 2x2 matrix, which is analytic everywhere except the blue bands, gamma J, they're bands. On these bands, they satisfy the jump conditions shown here. And so you see the jump matrix is this part. Well, sigma, all the sigmas are standard Pauli matrices. And also this solution should be, we're looking for solution analytic at infinity. And moreover, at infinity, it should have expansion as identity matrix and higher order terms. Please pay attention to this residue term, Y1, which is a matrix constant with respect to Z. Now, what is the function f? Here, it has a structure, some function, nice function of Z, plus these two terms, which contains x and t, and these terms make its solution, is related to the NLS. Okay, so now a few comments here. So first solution, NLS finite gap solution is just 1-2 element of this matrix Y1 multiplied by -2. Then the data for the finite, for the solution that we construct is just geometry of the contours gamma J and the function F0 that defines initial phases, right? That's all information. Now, how do we want to go ahead with solving this Riemann-Hilbert problem? Well, we can try to reduce the Riemann-Hilbert problem for the function y, for the matrix y to another matrix z, which will have constant jumps, constant in z. Right, and this is done in this business. This is done by using the G function, right? So the G function is at the moment unknown function, analytic everywhere except bands and gaps, and moreover, it has to have it must be analytic at infinity. So if we do the transformation, if we calculate the jump of the new matrix Z, you will see that it will have two kinds of jumps. On the bands, it is this. On the gaps, it is that. It's a result of calculation. Unfortunately, I don't have time to go in any details. But so how it makes it constant on each jump? Well, if we introduce, we have a freedom to choose function G, right? If we introduce the requirement, these two requirements on bands and on gaps, where W and omega are arbitrary real constants. They should obey Schwarz symmetry though, right? So then you see that this expression here will be a real constant, and this will be also a real constant. So the function G allows us to reduce the Riemann-Hilbert problem to the problem with constant coefficients. So now we have naturally two questions. So what is the meaning of the constants of omega and W that appear in the process of reduction? And then how do we define them? I will start with the second one. And to define that, we want to solve these conditions for the function G form a scalar Riemann-Hilbert problem for the function G, and we can solve it by well-known Sahotsky-Plimel formula. Immediately get this equation, this formula where R is the radical defining the Riemann surface. So alphas are all the branch points, all the end of the bands that you see. And now we have, if you look at this formula, you will see immediately that it's not clear that G is analytic at infinity, because R behaves like Z to the 2n+1 as n goes to infinity. So in order to maintain, or in order to arrange analyticity of infinity, we have to set some conditions. And these conditions are give us a system of linear equations on the W's and omega. And that is a system of linear equations that is a subject of our study, essentially, right? And by the way, it is clear from the properties of these coefficients involved here that there is a unique solution for this system. Okay, so now, by the way, this contours A and C's are contours around bands and gaps of the Riemann surface. Now, what are omega and W and omega themselves? Themselves, they're defining phases of the multi-phase solutions. But in this talk, we are not interested in a specific realization. We're rather interested in the wave numbers and frequencies, which are, and they are the derivatives of X derivatives of these constants, or T derivatives, or integer combinations of these derivatives, right? In order to understand better what combinations we need, we introduce, so all that I'm talking now is just linear algebra, right? But I will use some jargon of algebraic geometry here. So consider if you have a G function mentioned above, you can introduce two differentials, dp and dq, two meromorphic differentials on this surface known as quasi-momentum and quasi-energy. And then we naturally consider their periods over the loops around A and C contours, and this what they are, the same for the differential dq, similar expressions. And now we're looking at that, we define the wave numbers as this quantity, the wave numbers and frequencies, and the other set of wave numbers and frequencies as these quantities. They are not exactly that. As you see, they're a little bit different. And they're different because we want to go from the contours around gaps to the contours like B cycles here, right? So what you see are almost A and B cycles if you ignore signs, plus and minus. Okay, so now I have this. So now I can say that these quantities that I introduced, K's and omegas, tilted and without tilted, are given are just A and B cycles up to the plus and minus of the quasi-momentum and quasi-energy. Now, this choice is justified by observation that if we take an individual band and shrink it to a point, then the corresponding kj and omega j will go to 0, right? It's an easy observation. That's why we call these guys without tilde. We call them solitonic components of wave number vector. And the tilde we will call the carrier component. To illustrate what I mean, consider genus 2 solution, which has 2 wave numbers, and we just collapsed 2 bands, 2 points. You get a breather. So one of the wave numbers goes to 0, and then the other is responsible for describes the oscillations here. Okay, so now again we go back to the original equation with W and omega, and now I can replace W's and omegas by K and K tilde, omega and omega tilde. Moreover, I can take linear combinations of this equation to create polynomials instead of powers of zeta there. And so if I choose these polynomials wisely, if I take correct linear combinations, right? So namely, this Pj is the polynomial J's normalized holomorphic differential, omega j, which has Pj over R of z, R being the radical, right? So then this is the system of equations I will get. And actually, it's not a system. There is one system for k's and another system for omegas, for wave numbers and frequencies. So all that we need to do now is to get a large n transition to limit. I'm sorry, before doing that, we can separate real and imaginary part. Remember this k's and omegas are real numbers. So if I take real and imaginary part, I split the above systems into real part, imaginary part, and real part. And surprisingly, so you see, I sort of decoupled untilted components first, right? So there are no tilted components, and then tilted components can be just reproduced once you solve for untilted wave numbers and frequencies. Okay, so I want to mention that this phenomena is new compared to the KDV situation. You wouldn't have this tilted and untilted, right? You will have only analog of that one. Okay, so now thermodynamic limit. Well, for thermodynamic limit, we have, so we introduce centers of bands and half of the bandwidth. And we assume that the bands are filling some compact set in the upper half plane and complex conjugate, right? And then we consider the scaling. And you will see why in a minute, you will see why it's important. So we scale the bandwidth to be exponentially small with respect to the number of bands with a coefficient nu here. Now that is an exponential spectral scaling. Then we can consider sub-exponential, where the band is larger than exponential, and super exponential when the band is smaller. And that corresponds to the situation of condensate limit and ideal gas limit. We also can consider different setting when we collapse all bands, or maybe we leave one exceptional band. If we collapse all bands, we get soliton gas. If we leave one exceptional band, we get breather gas in the limit. If we leave two, let us say, exceptional bands, we will get what is called elliptic, or can be called elliptic gas, and so on. Okay, so now in order to move ahead, I need to calculate in this system, I need to calculate asymptotics of these coefficients. If you look closely, you will see that it's essentially asymptotics of Riemann period matrix in this situation. And that can be done by this. So that's a lemma saying that you will recover this formulae. So this is for off-diagonal elements. So when I consider the B cycle Bk, I take it together with its Schwarz symmetrical B minus K. That's how, right? So I can consider of diagonal elements, G is different from K's, and diagonal elements, G is equal from K. And as you see in diagonal elements, the leading order behavior is logarithm of delta J, as delta J is e to the power minus n, so that this theorem behaves like n, and this is a correction. And this more complicated expression here. I want to emphasize, so what is R0? R0 is a radical related to the band that is not collapsed, right? So that's R0. Similar calculations can be done for the elliptic or higher genus gases. They will lead to more complicated expressions. So now what I want to do, I want to take this asymptotic expression and plug in my system of linear equations, and then I obtain something looking like that. So you see that there is a big sum except diagonal theorem, and then diagonal theorem is written here. And then there is a right-hand side. So what I wrote here is just one formula for both wave numbers and frequencies. It depends what you put in the right-hand side. If I put just zeta, it will be wave numbers. If I put zeta square, it will be frequencies. So I get a big system of, again, linear equations. So there is a big sum that will get into the integral theorem eventually, and then there is off-integral theorem given by diagonal elements. So the integral theorem corresponds to the interaction. And so so in order to do this transition, one can scale this Km and omega m as some constant of order 1 divided by n, and then we interpolate these constants with a function u hat and v hat. So few comments are here. So if we have sub-exponential growth, so you will see that this theorem will become of smaller order because it wouldn't be n here, it would be something smaller than n, and it will disappear, and we will have only integral theorem. And the other limit, of course, if you have super exponential growth, then this theorem will dominate and we can skip the exponential theorem. Now, the other observation is that this expression here represents the formula for the phase shift of two Breezer interaction. That's the first time we know this formula is derived in such a concise way. In other more involved expressions were obtained by independently by Gilash and by Gina Biandini and their co-authors. Okay, so now there are some experiments done by Stefan and his team verifying that indeed these formulas are correct. And so if we go to this limit, to this thermodynamic limit, then the above expressions, if I ignore one more thing is that this term here becomes zero if the size of the exceptional band is also shrunk, right? Because when delta 0 is 0, that term disappears. So let's first consider simpler situation. If that the integral expression, integral kernel becomes simpler, we will end up with these two equations for what? So a known function u is this interpolant of the scaled wave numbers times the density of the bands. And same with the function v. Sigma is the ratio of the scaled density of the bands and the, scaled bandwidth divided by the density of the bands. So these two equations form non-linear dispersive relation because they connect essentially essentially the wave numbers and frequencies through the underlying Riemann surface. Okay, so now the question is, we need to study these two equations. So what can be said? Before that, so let me just show that in the case of the breather gas, so if both terms are preserved, we get more complicated nonlinear dispersion relation for the breather gas. And out of these two relations, we can easily derive equation of state, which is this equation. So how we derive them? If we denote S, the ratio of V over U, I don't know what it's doing. The ratio of V over U, so then you see this term is sigma times S times U, this term sigma times U. So if I multiply by S of eta, the first equation, and subtract, the off integral terms disappear, and that's what I will get. Now, if you remember talk of Benjamin Dayon, that was the one of the two equations that was central in his presentation. Some integral kernel times the difference of effective speeds times density of states. Okay, so everything has an exact meaning in our setting. Okay, so now a few words about solving these equations, for solving these integral equations. So first observation is that if you look at this term, it is nothing else but the green potential for the upper half plane of the positive Borel measure d mu. So d mu will be u times, I'm sorry, mu is abused, letter mu is abused a little bit, right? So that is, so this is d mu. And so equation then can be written in this way. So green potentials of the measure d mu times sigma times u, where u is the density of this measure, equals the right-hand side, right? So we will be studying this equation. Right-hand side will be defined by phi. Okay, so what is the idea? So we want to prove existence and uniqueness of solutions, and also that u is positive. Wave numbers have to be positive. And it would be good, Thibault, if you can advise me on the time.
So 1 or 2 minutes, because we started late, but yeah, maybe 1 or 2 minutes if you want to have some question, Alex.
Yeah, I want to have some questions, but 1 or 2 minutes wouldn't make it. So 3, 4 maybe, if it is right. Okay.
Okay,
so
I'll let you.
Yeah. So so first we consider sigma equals to 0. So there is there is only integral term. Then the equation has this form. And we immediately can notice that this is the earlier Lagrange equation for green energy functional. Green energy functional being defined like that. So green potential integrated, and the right-hand side, or external field, if you want, integrated and subtracted. And for this, for this situation, now we are within the realm of potential theory, and much is known, namely that the minimizing measure exists, and so on and so forth. Okay, so we want to extend it. So therefore, we want to modify the energy functional J0 to the case when we have sigma, right? To the case when we have non-integral term. And then we want so that the equation of interest will be Euler Lagrange equation. And then we want to understand prove the existence of minimizer, the meaning of density, and also we would like to understand the smoothness of all that. So, so the first theorem that part of my joint work with Arne is the following. So here is the modification of the energy, right? We just, to the standard Green's energy, we added another term which include density. If the measure is, if this measure is absolutely continuous, otherwise it's infinity. And then we can prove that the unique minimizer exists, that this equation holds almost everywhere on the support of, on the support of the measure, and of the support we have under the additional requirements on the right-hand side phi, that the equation for u satisfy and for v do not satisfy. we have this, this additional condition, and therefore what we obtained we call the weak solution. Now here is the point. I want to consider the following problem. Fix contour gamma, fix right-hand side, and let's play with sigma and allow sigma to vary. What happens? So what happens that we have, oops, I don't know what's doing. What happens that we have these inequalities that the on the condensate, when sigma is equal to 0, it minimizes the energy on the contour gamma, right, for the given right-hand side. And moreover, if we want to understand what does it mean, so what does this mean, this energy? Well, this simple calculation show that this energy is equal to the integral of phi d mu star. And if you remember that phi is imaginary of z, well, not remember, but we know that in our case, phi is imaginary of z, we found that this energy that we are talking about represents the average intensity of our Soliton gas with the opposite sign. Now, if we put some additional condition on the I want to.
I will have to interrupt you. I mean, you will have to conclude soon because I mean, I don't want to be too late for Manuela.
Okay, sorry. So, okay, so we can, under additional condition, we can prove that solution in the normal sense exists. And I will go skip whatever examples and other good stuff and go to conclusions. So first, what I would say that we consider exponential, sub-exponential, and super-exponential scaling kinetic equation are rigorously derived for Soliton and breather gases. Well, for Soliton gases, not for breather, because proofs do not extend at the moment for breather gases. And existence and uniqueness of solution was proven, and my performance was probably C+. Thank you very much. So it was hard to put it in 30 minutes.
No problem, Alex. Thank you very much for the talk. Thank you. So we have time for one very small question. Otherwise, we go to Manuela's talk and we can ask questions during the free discussion. Okay, so I see there is no question in the chat. So thank you again, Alex, and maybe we can ask the question during free discussion after Manuela's talk.